Hello and welcome to today's video. Today we're going to be doing number 78 subsets. So given an integer array nums of unique elements, you want to return all the possible subsets and it cannot contain any duplicate subsets. You want to return the solution in any order. Okay, so what I'm thinking of doing for a solution for this, we're given two examples, 1, 2, 3, and then we have 0. It's basically doing what the problem is stating, which is just creating a series of subsets and returning it as a final value. We can go ahead and do a visual example to see how we can get to that solution. So let's imagine we have a pointer starting at index 0 over here. And for this specific index, what we can do is we can add that. We can have a results array at the very beginning, and then we could have a cur to represent what's currently what we can currently move through. For here, we can either choose to add 1 to what we could have as the current subset that we're iterating through, or we can choose not to do it. So if we choose to do it, then we can go ahead and add 1 to the cur and then move on to the next index and then do it again. And then we can go ahead and choose 2 and then choose 3. Imagine if we choose all 3 combinations. Or we can go ahead and decide not to choose number 1. So if we decide not to choose number 1, we can go ahead and move on to the second one and add that. And then let's say we want to add number 3. So then you can add 3 as that. For that as well. So for that one, you choose not to add 1, you choose to add 2, and you choose to add 3. Now, what if you choose to not add anything? Well, you have this one, and let's say you choose only to have 1. So we have this, then 2, then 1, 2, then 3. So basically, we have a decision to make where we can either choose to have it as part of the current subset, or we can choose to have it as not part of the current subset. And we can go ahead and add this to the output or the result as we're going along and traversing and making the decision, and then we can have that returned as our final result. So to code this up now, I can go ahead and begin creating the results array, and then we can have a current array. So what we can do is we can define a function called backtrack, which you take the index from, and you want to start at index 0 before we return the result at the very ends. So from here, what we want to do is we want to check to see whether or not first we want to check to see if the index is out of bounds, because that's going to be our base case. So once you reach the end of it, you don't want the backtracking method to keep doing it, to keep going. So we can go ahead and check for that. If I is greater than or equal to the length of the nums, then you want to stop, and then you want to go ahead and just append the result. So we can go ahead and do res.append, and then we can do a copy of the current one over here. Now, for the next one, what we can go ahead and do is we can go ahead and we can go ahead for this one. If this doesn't happen, we can go ahead and just return this at the very end. So we want it to break from the thing and just have that ends. Otherwise, what we want to do is we still want to add it to the results. So we do res.append the cur. And then the next thing you want to do is you want to do a backtrack on the I plus 1. You want to do res.append of the cur, or you actually want to. Actually, wait, no, you don't want to do this. You only want to do this once you've reached the very end, and that's when you want to add it, because that's after you've made all of the decisions already. So what you would actually want to do in this case is you'd want to append the currents and the current value to the current subset. And then afterwards, you can call backtracking on I plus 1 before popping it. So this is our decision to go ahead and choose that element and then move forward in the index. And then we can make the decision to not choose it, nums I, And then we can go on backtrack again on I plus 1. And this should generate every single possible combination that you're able to for this one. So just to go back again, just explain this. We have our base case over here, which adds the results. In terms, it appends a copy of the current subset. So that's after you reached your end and you made every single possible decision. Yes, yes, no, no, yes, stuff like that. For here, we're actually appending the element itself, and we're making two decisions, either to go ahead and add the element or to go ahead and have it go forward, move the index forward without it. And then at the very end, we can return all of our final results. So we run this. Oh, go ahead and do a backtrack. Oh, right, yep. You pop it without specifying the index. Accepted all test cases. Let's go ahead and submit. And then we're accepted. So some things to note about this is that the time complexity is going to be O of 2 to the power of, O of 2 to the power of n, because you have to generate every single possible combination as you move along. So in terms of the space complexity as well, space complexity, it would also be 2 to the power of n as well, because you're generating every single possible combination and having that as part of the resulting output. So let me go ahead and just confirm this, or let's see if LeetCode allows me to. Yeah, okay. 2 to the power of n. Okay. Space complexity is actually O of n for this situation. Let me think about that. Oh, I see. 2 to the power of n. It will be 2 to the power of n. Oh, it would be O to the power of n because you're only adding to the results array at the very end of the iteration. So you're not traversing through and adding every single possible sequence. You're only adding it like the ending nodes, or like the leaf nodes, as you go to the very bottom and you made every decision. That's what you add as part of your memory, and that's what the final result is going to be returned as. So yeah, well, thank you for watching. I did make a couple of mistakes, but it's pretty late, so yeah.